This paper is a follow-up to the CLIP paper. In the CLIP paper, if you remember, we learned that you can do a joint embedding between text and images. And the way you train the model, just to recap, CLIP is contrastive loss image pre-training. You pre-train the machine or the model by taking image and text, image and caption that go together. It was done by harvesting the web, Instagram and the web and so on and so forth, because there are situations where you can find such data to be coexisting, and where you find text and image that go together, coexist, image, captioned image, you harvest it. Now, the limitations of that paper of CLIP model were, A, that the captions are small text. Secondly, the data was very noisy because people do all sorts of irrelevant text captions to their images, and that affected the quality of the model that arose from that. Nevertheless, CLIP is deeply influential, heavily used. Some variant of CLIP is heavily used. People knew that they are looking at something big, and there was a subsequent effort to improve upon the groundbreaking work that CLIP had done. We'll start with this paper, BLIP, and follow it up with BLIP 2. But to get to BLIP 2, we should first do a BLIP, because it makes two significant contributions. Both of these contributions are significant enough that one could have plausibly argued that there should have been two separate research papers, right? One following another on that. Nevertheless, it is there, and we are now going to do this paper. So now this paper will do in considerable depth. The CLIP was, because we had background on it, we understood what contrastive loss is. We understood a vision transformer. It was a straightforward idea. It is putting two big ideas together. Use vision encoders and bring in contrastive loss. And once you do that, pretty much CLIP becomes straightforward. This particular paper sort of continues the work, but in a very interesting way. It builds an architecture that is, and you can see the use of the words like vision language pre-training, VLP, and vision language models. And you will see as we move forward, people begin to use the term visual language understanding, right? Those terms began to emerge and more have become part of our common vocabulary. Today, there are entire sites devoted to curating the best papers and research works and projects on visual language understanding. VLU is a big topic. In companies, there are entire teams devoted to VLU. Are we together? Right. And research groups and model builders and many things are devoted to it. Right. So let's read this paper carefully. Before we read this paper, I'll just give you a glance of where we are going. This is the main picture, the main architecture of this paper. Right. As you can see, there are 4 pillars in this. I will just mark those 4 pillars. Pillar number 1, pillar number 2, pillar number 3, and pillar number 4. Are we together? And it will take us some time to make our way through these different pillars. So clearly, it's a much more complicated architecture than the CLIP one. Right. What does this paper say? Let's read the abstract. First of all, it uses the word CLIP has become BLIP. It says bootstrapping language image pre-training. So the word bootstrapping is somewhere. And bootstrapping usually refers to starting from the ground up in some sense. And it says bootstrapping language image pre-training for unified visual language understanding and generation. So an interesting aspect of this is, do you see the new word come into the process? Generation, right? So it is not just an encoder-based model, it has a generator built in. So we are going to do that. And it's a vision language understanding or visual language understanding. It does it in a very interesting way. And what is it that we are going to do that? So let's read the abstract carefully. And this, guys, is a very important milestone in our field. So let's be careful in reading this. Vision language pre-training has advanced the performance for many visual language tasks. So far. However, most existing pre-training models only excel in either understanding-based tasks or generation-based tasks. Understanding is like the encoder kind of thing, right? It understands what that image is, right? If you remember with CLIP, we could create embeddings, and those embeddings were meaning aware, semantic aware. You could give a textual search into the space of those images. We did that. We took the images that we got from Unsplash, and we searched through that using this. So, and then there are things that are generative models, right? So we have some basic models that can generate, let us say, pictures, right? Little diagrams. We haven't covered that, but we'll cover that. But these two kinds of models exist. The latter are decoder models, usually generative models. The former are encoder models. Now, let's see what this paper says. Furthermore, so I hope we are clear about the meaning of the first. It summarizes. And in this one sentence, it brings out the limitations of prior work. I hope we are clear about that, right? Generation tasks, right? So this is it. You either do one or the other. Furthermore, performance improvement has been largely achieved by scaling up the dataset with noisy image text pairs collected from the web, which is a suboptimal source of supervision. What could they mean? More data has led to improved models. Nevertheless, that data set were quite noisy because those image text pairs collected from the web, they are a suboptimal source of supervision, means the quality of the data for supervised learning is not good. Ideally, for supervised learning, you would want your xi and yi to be matching, right? Input and output to go together. You don't want to tell the machine that yi is what you predict for xi, and then you give it data that's essentially gibberish. That is it. Furthermore, performance improvement has been largely achieved by scaling up the dataset with noisy image text pairs collected from the web, which is a suboptimal source of supervision. In this paper, we propose BLIP, a new visual language pre-training framework which transfers flexibly to both vision language understanding and to generation tasks. So see that. They are spanning both of these two worlds, right? Visual understanding as well as generative tasks, right? So that is the key contribution of this paper. It is to say, we propose BLIP, a new framework which transfers flexibly to two tasks. BLIP effectively utilizes the noisy web data by bootstrapping the captions. So I told you that we get images and captions, right? It bootstraps the captions where a captioner generates synthetic captions and a filter removes the noisy ones. So what they say is that this model has one virtue. Given an image, it will produce good captions for it, right? So it has a captioner. That is a generative task, isn't it? Generating a caption for a model, for an image. And then there is a filter which removes the noisy ones, bad captions. It will be able to eliminate bad captions. So that looks very promising. And it says that you can do it in a bootstrapped way. Namely, you can start with those noisy images and their captions, learn from that. See, this is very interesting. You learn from that, you build a model, and having learned the model, it can go back and correct the data. Isn't that lovely? And augment and correct the data.
How many captions does it generate for the images?
Oh, it can generate as many as you want, but you just want one, right? One good caption. But you can ask it to generate over and over again if you so wish. So let me mention this. Let us say that you have a data set, right? You have an image one, and you have a caption. Let's say you have a caption text one. You have an image two. You have a caption text two. You have an image three, and you have a caption T3. And let's say that you have image 10 and you have caption 10, right? And you have caption 9, text 9. Right? Suppose you have this situation. Let us say that there are errors in this and this. Now, see, remarkably, and let us say that you also happen to have some images which don't have caption at all, right? So this machine is going to do two things. One, it will have a captioner. What will the captioner do? It will, suppose you have an 11th thing, it will go and add a good caption, T11. A generated caption, once it is fully trained. And the second thing it will do is, it will replace these two images, these two texts, and potentially replace them with better captions. Does that make sense, guys? It can replace with a T3 prime and T9 prime, better captions.
Based on what?
Yeah, that's it. How does it do that? That's a big mystery. Right. But if you make a claim that a machine can learn from noisy data and then go back and fix the data, that's amazing, isn't it? That's quite amazing. So before I go into the paper detail, let us see if it is actually able to do that.
Is this doing in the
Training stage itself? Yeah. So yeah, and then so we will learn from it. We'll see the steps. Font, bigger fonts. Huh? Okay. Let me see. Is this better? So guys, look at this figure 4. Examples of the web text, TW. So TW is what, the caption that came from the web, in this raw data. And look at the caption that the machine produces. Obviously, it is not necessarily always good. Right? It can also make mistakes. So look at the first picture on the left. What do you see? Birds over a lake, right? But the web caption said, from the bridge near my house. That caption makes sense. Somebody took a picture from their house, from a bridge near their house, and it's relevant. But it is not a good description. It's very subjective. It's not a very good description of the image, is it? From a machine learning training purposes. Come again?
Is the bridge not visible there?
No, bridge is not visible. Yeah.
It's a perspective which
Yeah, that is right. See, if I am the person, if I live somewhere and I have a bridge, and from the bridge I can see this image, to me the caption makes a lot of sense.
Yeah.
But is the caption descriptive of the image in an objective sense?
Exactly.
It is not descriptive of the image in an objective sense, isn't it? So if you are training the model, you don't want to train the model to say such things as a bridge near my house. You want to train the model to say a flock of birds flying over a lake at sunset, isn't it, guys? Right? And this is the beauty of this. This model learns from the noisy data and it ends up producing better caption. So you would agree that for the left case, this case is a winner. Would you agree? This is a winner. Now let's look at the second one. The initial caption says, in front of a house door in Reichelfels, Austria. That gives you the location of the image, but it doesn't quite describe the image. You would rather say a potted plant sitting on top of a pile of rocks. So once again, this is a winner, right? But this model, how does it do? Let's look at the third one. It says the current castle was built in 1880, replacing a 9th century wooden castle. Some European castle. Obviously, it is very informative about the image. But the interesting thing is that doesn't tell you, it is not, see, it gives you the context of the image. It doesn't describe the image, isn't it? The machine instead says a large building with a lot of windows on it, right? Now, you can say that in a way, the machine generated caption is inferior because it loses the context, but it gives you the description. So this is something to remember. You're training the machine to align with the image, understand the image and describe it in words. So the image and the word should mirror each other in meaning. Semantically, they should be aligned. So this machine does align, it does do the job of aligning this model. Nevertheless, sometimes you lose important information, right? Because alignment in meaning can lose you the context, important context sometimes. So this is it. Let's go and look at a few more examples. And yeah, go ahead. Yeah. I mean, the people, now we don't need to, this is very mature now, but in the beginning, yes, when this model was being trained, very much so. So now let's go through a few more examples, because I think once we get the examples, we'll see the value of this contribution. Look at the picture and the top left, first row left. The caption says, a week spent at our rented beach house in Sandbridge. Sandbridge is what, some British ties, perhaps? I don't know. No idea. But whatever it is not it is giving you the context of the image rather than the description of the image, isn't it? And would you agree that the model's description is more aligned? An outdoor walkway on a grass-covered hill, right? Look at the next one. It says, that's what a sign says over the door. So these are real examples, of how this model improves. The car is driving past a small old building, far more descriptive. Yeah. Next one, hand held through the glass in my front bedroom window. Again, it's a context rather than a description. A moon against the night sky with a black background. So guys, remember, this is 2 years ago. At that time, this was a breakthrough, right? And we will see how this model works. See, the nice thing is at that time, people used to reveal their models. And nowadays, companies like OpenAI believe that their name has the word closed in the title instead.
That's why Elon Musk filed a lawsuit.
Right, yeah. So the next image, the bottom row, a stunning sky over Walney Island, Lake District, July this. Again, a context, but a much better description is no. So this time it gets it wrong. It says an outdoor walkway on a grass-covered hill. No, I think this is not a problem in the model. This is probably a typo in the paper itself. My own guess would be, this would be a typo coming from the paper itself. I would be very surprised because there is neither walkway nor grass. It's just the previous, you know what happens when you write paper, you get. Yeah, exactly. So, which is why I'm saying that the people, when they were writing it, they just copy pasted it without realizing it. Okay, so this one is suspect, yeah. Then the next one is living in my little white house. A tiny white flower with a bee on it and a pink rock from below. Where is the pink rock? I don't know. In the lower right, can anybody see the pink rock? I suppose the pink rock is this one. Perhaps. That's the closest you can come to the pink rock, if there is such a pink rock. I can't see one. But in any way, some colorful trees that are on a hill in the mountains. Right? Good. Perhaps it could have gone further and said fall colors. Fall colors on a hill. But it didn't. So, by the way, models have improved. Things have been moving forward. But see, guys, do you realize that this paper, the ability to do this, to add generative tasks to what CLIP could do, is a game changer. isn't it? You can generate captions to images now. You have a captioner. And because you have a captioner, it also means that you have a filter. You can tell whether a caption that exists is aligned. If it is too far, if the cosine distance between your caption and the original caption are too far, it probably means that the original caption is wrong, isn't it? Right? So as always, the new dictum is having to choose between machine and man. Unfortunately, most of the time you have to trust the machine. Okay? So I was giving you, so with this background, I hope you realize that what we are looking at is something that represents a significant advance. Let's study this paper then. Let me go back to them. So we go back here. It says, now let's read the sentence again. In this paper, we propose BLIP, a new VLP framework which transfers flexibly to both visual language understanding and generation tasks. And guys, did we understand the root of the word bootstrapping here? Because it learns from noisy images and then goes back and fixes it. Noisy image captions and fixes it. Bootstraps it. It has a captioner and a filter. The two contributions are captioner and a filter. Removes the noisy ones. We achieve state-of-the-art results on a wide range of vision tasks, such as image text retrieval. This is a search bot. Remember, retrieval is a search, right? Recall it one. Image captioning, again, it beats the state-of-the-art by 2.8%. Visual question answering by 1.6. These are pretty significant advances, but more than that, so these numbers are obviously represent advances. More than that, the fact that you can do this was quite noticeable. BLIP also demonstrates strong generalization ability when directly transferred to video language tasks in a zero-shot manner. Means it's not a model that has memorizes, generalizes. It has actually learned. And so you can give it some random image, it will describe it. Right? You give it a completely new image or you give it a completely new text, it can do a pretty good job of it. And one final nice thing is code, models, and data sets are released. If only all companies did that. Hint, hint. Right? Okay, so we go to this paper. Vision language pre-training has recently received tremendous success on various multimodal downstream tasks. However, existing models or methods have two major limitations. Let's look at the limitations. Model perspective. So they will look at it from two different perspectives, the model perspective and the data perspective. From the model perspective, most methods either adopt an encoder-based model or an encoder-decoder model. Encoder-based model, did we encounter one a little while ago? What was that called? And clip. Yes, we did clip. Or you use an encoder-decoder model. However, encoder-based models are less straightforward to directly transfer to text generation tasks. See, encoder-based models can be used for text generation, but they do poorly. You don't use BERT to chat, right? For example, right? Those are decoder models. Whereas encoder-decoder models have not been successfully adopted for image task retrieval tasks. On the other hand, if you use something whose tail end is a decoder, they don't do well on retrieval tasks because the logics coming out of them, remember, they are not trained using contrastive loss and things like that. So that's a model perspective. Because decoder, what is the loss function for a decoder? You will have to use a causal loss. Like I'm expecting the cow jumped over the moon and you are saying the horse went to the meadow, right? So then there's a loss between what I expected and what you gave, which is different from the sort of contrastive loss that you train encoder with. So there's a fundamental disconnect. Now, from a data perspective, and this is interesting, most state-of-the-art methods, CLIP, ALBEF, and SIM-VLM, consider this, if you're enthusiastic, consider reading these models too. I'll leave that as an exercise for you. Pre-train on image text pairs collected from the web. Despite the performance gain obtained by scaling up the data set, our paper shows that the noisy web text is suboptimal for vision language learning. We just saw that, right? We are training our machine. See, we always trust the data. With the data, if it is too noisy, it impairs your training. Just getting more data gets you a little bit more performance. It begs the question, why not also go clean the data? That's a data perspective. So to this end, we propose BLIP, Bootstrapping Language Image Pre-training for Unified Vision Language Understanding. And guys, do you notice the word that I like that is much more contemporary these days? Vision Language Understanding. Let me put it there. VLU. Vision Language Understanding. Right? So this model belongs to a class of vision language understanding. BLIP also belongs to that class. So BLIP is a new VLP framework, what is VLP? Is a new framework which enables a wider range of downstream tasks than existing methods. So now let me look at this. It introduces two contributions from the model. By now, guys, you must have noticed that all the papers we are reading, in the introduction, they always have an important section. What is that? They mention what the key contribution is. All papers that we have been reading recently, do they have this in the introduction? Key contribution. It's now more or less a convention in our field to have this section. And let me highlight this here. First one, it says, multimodal mixture of encoder and decoder. So they are saying they are going to use multimodal encoder and decoder all there in a single model. A new model architecture for effective multitask pre-training and flexible transfer learning. What in the world is transfer learning? You train it on some generic set of tasks, but then now you can use it for whatever other downstream tasks, right? We are in the world of, the whole pre-training is the first part of transfer learning. The second part is use it. If it doesn't work, fine-tune it, right? So you create a model that is amiable to fine-tuning. Or another way that you could say for pre-training some of these important models, you often say these are foundational models. So they call it MED, and MED can operate either as a unimodal encoder or as an image-grounded text decoder or as an image-grounded text encoder. Oh boy, big words. What do they mean? This architecture can act as a unimodal text encoder. Means, unimodal encoder. Unimodal encoder is what? You give it an image, it will create a vector out of it. You give it a text, it will create a vector out of it. That is unimodal encoding. Are we together? It can also do, so there's a lot packed into this unimodal encoder. We got it, right? Text to e-text. Image also to e-image separately, right? Doesn't matter whether you give it a text or an image. And therefore, it's a single mode. It will give you just one modality. It will convert it into an image grounded text encoder. What does that mean? Means, suppose you have an image already there that says something about the text. In that situation, don't you think you should borrow some of the understanding from the image when you create the vector embedding of the text? Isn't it? Because this text is contextualized by this image. And so you can create a vector embedding that is contextually aware, that takes the semantics of both the image and the text together. That is what is meant by this statement, image-grounded text encoder. Right? So it will create a vector embedding that is sensitive, not just to the text, but to the image. And this is multimodal embedding, isn't it? Right? Because it's a jointly taking information from the image and the text to create the embedding. And lastly, an image-grounded text decoder, which means if you put an image and now you say, and there's an image of a cow jumping over the moon, and then you say, what is the cow doing? it should say jumping over the moon. Right? So something like that, right? So image grounding. Right? Because without that picture, what is the cow doing? The more likely answer would have been grazing in the meadow. Right? So that's a difference. The model is jointly pre-trained with 3 vision language objectives. So there are 3 objectives. When they use the word object, so this is, by the way, a lot of research language or academic language. Pre-trained with 3 vision language objectives means what? Here, the word objective is synonymous with loss functions. Right? Objective function, loss functions are synonyms. So one is, so let us look at these 3 objectives. So 3 objectives means 3 i.e. 3 loss function terms, right? Loss function terms. 3 things. What are those? Let's look at that. First one is a contrastive loss is image text contrastive learning. Have we ever encountered image text contrastive learning? Just that. That was CLIP, right? Remember? CLIP. So basically what that was literally the loss function for CLIP. Right? If I remove the word learning, I just call it the loss. It is literally the CLIP loss function. It is the CLIP loss term that we encounter. Number 1. Number 2, that it says, so this is this part, right? Contrastive. Second is image text matching. What does that say? If I give you an image and I give you a text, you have to take those 2 things and tell the probability that these 2 things match, right? Probability that the image, the text match, right? Now, suppose that image and the text do actually match. They come from the same caption, the image and its caption are there, then the probability should be high, isn't it? Otherwise not. So the probability should be high when I give it. So for it to have that ability, what is the loss function that you use for such matches? Negative log likelihood, because you can do minus log p. Right? This is your prediction, right? Another is minus log y hat. For that. That is your matching function. Very good. Good. You guys are picking up. Is it because you're in the intro class? How many of you answered this question? You answered, right? Who else answered it? Are you guys in my intro class? Yeah, that explains it. We covered it there, isn't it? The next is image conditioned language modeling. This part is, if you ask it to tell what is this image about, the text that it produces, does it align with the image? Isn't it? So that is your standard causal loss. Right? The image conditioned. If you remove the word image conditioned, the standard is just the language modeling loss. That's your standard decoder loss function, right? Sort of adaptation of the standard decoder loss function in the transform. So guys, are you having fun reading this paper carefully? You see, there's a lot packed into the sentences. So that was only one of the contributions. And then it goes on to say there is another contribution, captioning and filtering. A new dataset bootstrapping method for learning from noisy image text pairs. We fine-tune a pre-trained into 2 modules, a captioner to produce synthetic captions given web images, and a filter to remove noisy images from both the original web and text. This should be easy, right? If we can create a model that can produce good captioning, then the filtering is implicit. So lovely. You can imagine these guys had a lot of fun doing this. We perform extensive experiments and analysis and make the following key observations. So they make 2 key observations. We show that the captioner and the filter work together to achieve substantial performance improvement on various downstream tasks by bootstrapping the caption. What in the world could that mean? The captioner and the filter work together to achieve substantial performance improvement on various downstream tasks by bootstrapping the captions. We also find that more diverse captions yield larger gains. Enlighten me. Take a stab, enlighten me. What could this mean? Anyone, guys? Throw darts into the dark. It's okay. Make a guess. What does this paragraph mean? I'll just highlight this paragraph in a different color. Explain to me, what in the world are they harping at?
They're taking the. So they're taking the based on the captioner and filter, they are kind of generating those new captions, but also feeding it back to the image to make it.
Very good.
To make the model pre-train better.
Yeah, so it's a multi-pass, it's an iterative solution. First time what you do is you take this model, you give it this image and you give it noisy data. It will get trained. If it gets trained, so look at this way. Let's do it step by step because this is fun. It's like having your cake and eating it too. Noisy data is there. You feed it into pre-trainer model, pre-trained, iteration 1. Iteration 1, this gets trained. Now what can you do? So this was pre-training phase, right? Step 1. Step 2. So this is, remember, this is our training, model training phase. Take, and let us say that this produces model M1, right? You can do this. You can take images. You can take this data, image, feed it in. You can generate caption. This is inference phase, right? Inference. You go into the inferencing mode, give it an image, have it produce the caption. Images that don't have caption, you can put caption. Images that have bad caption, you can fix the caption. Isn't it? And so what will you end up with? You will end up with better data. Let me just call this noisy data D1. Right? So now you have created cleaner data. Isn't it? Now what can you do? Step 3. Guess what can you do? You can feed it. You go back into the pre-training mode, the training mode, and you feed it into this. And then what will you get? M2. Then again, you can go into the inferencing mode. You can give it data D1. Oh, which was D0 or D1? That one, D1. This has to be D2. You give it the second iteration of the data, cleaner data, and do what? You again train this model.
This is also kind of effort and the backpropagation to do this in the mood.
Yeah. Yeah, inferencing, right? In inferencing mode. And then what do you get? you get whatever captions, and this will give you this. The output of this is D3, isn't it? So better data leads to better model leads to better data, and you can keep going back and forth. Does that make sense, guys? That is the meaning of the word. Bootstrap with noisy data, but then keep on improving it. Right? Doesn't it look like fun, guys?
How do you stop that? Like, so how do you know, like, okay, this is done?
Oh, usually it is the infrastructure team saying, stop having fun now.
Okay. Good one.
They'll take their hardware back. So these are the realities, right? So here we go. Now we understand this blue statement, isn't it? And what you can do is you can actually, given an image, you can actually ask it to generate caption and caption, 2-3 captions. So from one image, you can actually one image caption pair. As you fix it, you can actually generate more data, isn't it? You can create the same image and many different captions, and therefore you have lots of data, right? So it's a generative process. Next point, they say, BLIP achieves state-of-the-art performance on a wide range of vision tasks, including image text retrieval. That is obvious, right? For search engine. Isn't that, guys? It can do everything CLIP can do. Definitely, right? So search, because it can create embedding vectors out of images and out of text. So therefore it does that. Image captioning, because it's a generative model. So can it do image captioning, guys?
Yeah.
Obviously it can do image captioning. Visual question answering. You could literally do that, because what you could do is give it an image and for text, just say, what do you see in this image? And whatever text is the output, that hopefully is your answer to the question.
How is it different from caption?
Because it's a question. It's a question. It's not a description of the image, but asking a question. Is there a horse there?
There will be no description like this.
Yeah, that is a visual question answer. So usually in multimodal learning and computer vision, visual question answering is a category of tasks. Yeah. Yeah.
In the first, when you do noisy data, you're just giving the caption or you're giving what image caption?
Image and caption.
Image and caption. You get that usually. And
Yeah.
the M1 output is 3.
The first model that got trained.
Oh, that's the model.
The first blip. It is blip iteration 1. So this is blip iter.
Then you get image again
Yeah.
to the model, then you get the caption.
Caption. Second time you just give the image and get better captions. Right? And then now that you have, that will lead to better data, D2.
It is image plus caption.
Image plus caption.
Yeah.
And now that you have image plus caption, you can go pre-training the model again. Right? So you keep seesawing between that.
I think one question. So in the first step, right, it's noisy data. So
Yeah.
that means your pre-training, how do you say that, okay, there is, the loss has gone down, and then you should stop training in that case?
Oh, that is a loss function. See, you go with the assumption.
Itself is noisy.
Yeah. But machine doesn't care, right? See, think about it this way. It may be noisy. Let's say it has 20% error rate or 30% error rate. Actually, I believe somewhere they say that it had as much as 30% error rate. Nevertheless, there is signal. You have to learn from the signal, right? Some of the captions are right.
No, as long as there is some stability to loss.
Oh, yes. The loss, if you look at it,
I think I got it.
loss and iteration, the model steps or rather steps of training, you will see it goes the usual classic path, right? It does show the normal expected behavior. So good, you guys are asking questions. It means you guys are, yeah, go ahead.
One thing you mentioned that like the image kind of segmentation. So who is there in the image?
Yeah.
Right? So, but in a single image, it's a single time it's something. More than okay.
No. See, it is not a thing that is exceptionally well at segment. When we do semantic segmentation, it means putting the boundaries on the
Yeah.
person. It won't do that, but it will just tell you For example, it will just basically say if John is in the image or horse is in the image. Sorry, if a horse is in the image.
Or based on that.
No, you can just feed it once the model is trained, you can give it an image and say, is there a horse? And it will say yes. Right? So you could do that.
Is there a way to see all it stores for that image to an image?
All that it?
All the description, whatever we call it.
We will see that. Yeah, we'll see. We literally saw that. Huh? So for example, here's an example. And by the way, you play with this. I want you guys to, so this is your homework for today. Get clip you have already played with. I've given you the Jupyter notebook. Nevertheless, go to Hugging Face, get clip, right? Use it because it's an encoder only model. It's limited. You can use it only for semantic search, but do that. But this model, like, download and give it your images. Ask it to generate captions. See what it generates, right? See, like literally, this is it. And every time you can ask it to, and then ask questions. Ask it, for example, is this a moon or a football? Right?
Now I'm getting the Google Photos and Apple Photos probably using this.
Yeah.
Oh, whenever I search,
Yeah.
I saw description.
When I release this.
Guys, this is the purpose of this course. All that was magic should become understandable now. And you should be capable of that. You know, there is a statement from Arthur C. Clarke, I believe, who said that anybody remembers the quote? A sufficiently advanced technology is indistinguishable from magic. Right? So you guys have to become so good at this. Others perceive you as magicians. Yeah, go ahead. Sanjay.
The 2 rounds are good enough. I'd like to try to do more rounds.
Oh yeah, people do more rounds. So you keep on doing a few more rounds. So nothing stops you. See, ultimately you'll reach a saturation point. When you reach a saturation point, you stop. Right? So I was joking when I said that ultimately IT will give you a call. Right? But in reality, you do reach a saturation point.
In the first step, I mean, just going on back to what I was saying. So you don't really want to validate also. I mean, try it on a validation data set. You just keep going because when you pre-train.
See, the thing with pre-training is that validation is very, very hard because we are talking of hundreds of millions of images, a billion image text pairs. So to do a split on that is a little hard, but nevertheless, you do validation because you do maintain some goal data set and you make sure that the caption produced is very similar to the caption in your goal data set. But you can't do like in standard machine learning, you do 70-30 split on your data and you do validate. Those things are a little bit harder because first of all, your initial data set is noisy, but you can do it. And this paper, I have to look into the finer details. It's been a long time, more than a year since I read it, but it is there. I mean, I read it long ago when it had just come in. So as you can imagine, much water has flown down the river. I can try to remember it. Okay. Yeah.
What do you call these clip and blip tabs?
These are all visual language understanding, vision language understanding models, VLUs. They come under the category of VLUs.
The way I look at it, the 4 fundamental papers were attention, word, and sentence word, and VLU. I look at that as a word, basically. Before I kind of build over.
Yeah, they all keep, see, science is accretive, research is accretional process. Right? Everything builds on what has come before. So this certainly builds on it. And you will notice that these guys, they themselves followed their own work with BLIP 2, which is well established, right? And we'll come to it. But enjoy BLIP while we are doing it. I notice some of you are taking breaks. Please stay with me to finish this paper. Oh, you guys need a break, is it? No. All right. So visual language, visual reasoning is their visual dialogue. We also achieve state-of-the-art zero-shot performance, which is zero-shot performance, by the way, these days, we don't speak about it much, but in those days, oh, wow, you can do zero-shot learning, zero-shot. Without any label data, you could tell this, tell that. Used to sound like magic. Today, well, right, of course. Why is it your machine is not capable of zero-shot? Right? We think differently.
Zero shot prompting.
Zero-shot prompting, yeah, exactly. So we also achieve state-of-the-art zero-shot performance when directly transferring our models to two video tasks: text to video retrieval and video to care. This statement, by the way, is really important. This zero-shot performance is very important. Yeah, because they never train the model on videos.
Yeah.
Nevertheless, it starts working on videos. Imagine that you only trained it, the only training data were images and captions, and yet it works on videos. Isn't that?
It converted into images.
Well, you pretty much decoded it. So what happens is that a video is nothing but an audio file, audio stream, and a sequence of frames. So you can say, well, it sounds magical, but when you think about it, it should have worked. It should have worked, right?
And obviously, because well-expected.
Yeah, that is true. And so this is it, guys. So, I mean, see, people write papers and then they feel great that it can do that. But obviously, this is certainly not its biggest contribution, right? All right. I'll ignore the related work, etc. Let me ignore it. Let's go to the method. So how do they do that? So we have done the introduction, related work. Well, I'll leave it to you to read. We propose BLIP, a unified blah, 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 and then delineate cap filt. So the captioning and filtering, they call a new feature called cap filt for dataset bootstrapping. Model architecture. We employ a visual transformer. What was the visual transformer? Did we do that paper? VIT paper, right? The 16 by 16 pixel patch, which divides an input image into patches and encodes them as a sequence of embedding with an additional CLS token to represent the global image feature. This statement, guys, I want one of you to unpack it for me. By now, you should be quite capable of understanding every single word here. In the visual VIT paper, what do? You take an image and slice it up into 16 by 16, right? And then what is the CLS token? Remember, Bert, you always prefix it with a CLS token. Exactly. And it represents the global image feature, like it, because it will tell something about the whole image. If it is meaningless, there is no way it can pay attention to one word more than other. Preferentially, it has to pay attention to the whole meaning of the sentence, right? So compared to using pre-trained object detectors for visual feature extraction, using VIT is more computationally friendly and has been adapted to these things on scale. In order to pre-train a unified model with both understanding and general capability, we propose multimodal mixture of encoder, decoder, a multitask. So what are the pieces? It has three main pieces. Unimodal encoder, which separately encodes images and text. The text encoder is the same as BERT, right? BERT, where a CLS token is appended to the beginning of the text. Likewise, an image encoder is your basic VIT kind of thing. And then when you throw in the contrastive loss term, basically it becomes clip. Right? But okay, let's leave that. VIT, just like in clip. Image grounded text encoder, that is something new here, which injects visual information by inserting one additional cross-attention layer between the self-attention layer and the feed-forward network for each transfer block of the text encoder. So this, it's very hard to make meaning out till you look at the picture. When you look at the picture, it becomes obvious. And therefore, I spend a lot of time on the picture now. A task-specific encoder token is appended to the text and then blah, blah, blah. Image grounded text decoder. Also, decoder is the second part of the thing, right? Which replaces the bidirectional self-attention layer in the image grounded text encoder with the causal self-attention, etc. So all of these are big words. Let's go and look at it. First, let's look at the three loss functions. Image text contrastive loss. Image text contrastive loss you have already encountered, right? It's your standard clip kind of a thing. Image text matching loss, again, probability that you want the probability of these two texts being similar, image and text being similar, to be high when they genuinely, the ground truth says they are the same. Yeah. Language model loss achieves the image-grounded text decoder, which aims to generate textual descriptions given an image. It optimizes a cross-entropy loss, which trains the model to maximize the likelihood of the text in an auto-regressive manner. See, a lot of these things, guys, when you read the paper, it looks very cryptic. You have to know beforehand. So you know a decoder model in a LLM, that's how you train. What do? You use a cross entropy. I mean, I expect the word, the cow jumped over the moon. I got the horse ran in the meadow. Now, token by token, for every token, I said the cow, but it said the horse. Now, between what was the probability of a cow? Much lower than horse. I can apply cross entropy loss to that term successively, right? So it's an autoregressive because decoders are autoregressive. The words that you produce feed back in to produce the next word, help produce the next word, along with the input, right? So that is all that they are saying. And simply put, it is your decoder loss, right? That's all it is. Okay. Now, before we go into that, model pre-training, dataset bootstrapping, a lot is happening here, but let's go back to the main picture and try to understand it. And if you get this picture, you would understand a lot. So let's go into this picture. First things, let's start in this direction. Do we understand this? What is that, all those white framing on the picture? Patching. You feed it. The first layer that you looks like your typical VIT encoder, isn't it? Right? As simple as that. Right? It's just an encoder. What will it produce? It will produce its own vector. Right? Now, look at this. You have another pillar. In this pillar where it says cross attention, ignore it. Ignore it. It doesn't exist. What does this look like? This looks like your standard BERT. You give it a text with a CLS. It goes in, it produces a text vector. So this will produce an image vector. This will produce a text vector. And what is this ITC there? Image text contrastive loss, right? So you basically say maximize if the image belongs to the text and the text go together, the text, maximize similarity, isn't it? That's all you're saying in this picture. So far it looks like clip.
Just a process flow box or is something else?
No, it's just it's the architecture. So you're saying it's the main architecture, right? So this looks like your BERT kind of a thing. This looks like, again, your VIT. It flows through, right? Now, the third and the fourth pillar are interesting. That's where something begins to happen. You notice, pay attention to this weird block that you have not encountered so far. You pay attention to what I just highlighted. Right? What in the world is this? What's that?
Image.
We heard about self-attention cross encoder. What is cross attention?
Yeah, cross attention. Yeah, it's very, very interesting. It's nothing actually remarkable. What you do is, remember in attention, your KQV, V comes in, right? Cross attention basically says that what comes out of here, this side, right? Treat it as your Q and take this output here. What is the output? Image. This image, I can take the image vectors and break them into K and V and Q. Ignore the Q part of it. So when you do the attention formula, take the key and the value from the image and take the query from this part of the text. That's all. Right? So here, throw away the key value and take the key value from the other. Why is that? Because what you want to do is you want to make the text pay attention to the image. Right? So, do you see that? So I gave you this picture. Suppose there's a picture of a cow jumping over the moon and the text is, what's the cow up to? Yeah. It can figure out jumping over the moon only if the text is paying attention to the encoding of the image. Isn't it? The key value coming from the image. That is all cross attention is. Beautiful, isn't it? That is it. So actually, cross attention is built into the original transformer itself. When we discuss it at that moment, I didn't quite emphasize that. See, whatever the encoder produces becomes the KV for the decoder, because the decoder takes the so far produced words and gets those words pay attention to the encoded information. Right? So coming from the encoder. So it was there. So this is cross attention. So now what will happen? See, notice the same text went into two directions, here and here, except that here you have prefixed the word encode. Just a mechanics of it. And now the main thing is not that you have put instead of CLS, you have put encode. The main thing is that you have done cross attention here, whereas on the second pillar, it was just a standard word. Right? Except that here, the only additional step is you do. So what people do is they keep the cross attention layer there based on the same thing, the same values. But what they do is they first do a pass with cross attention, one pass without cross attention through the same pillar, right? You get two different outputs. That's all they do. Yeah. So that is it. Now, then it produces its own vector. What is this? ITM. It is the image text matching. Because now this will also produce, ultimately it's an encoder, right? It will produce a hidden state, CLS state, the encode state, vector for the encode. And you can then apply a probability, a softmax to this and negative log likelihood laws to say, well, I needed a high probability. It was about the cow, right? So that's that. So that part is easy, right? So we already have had two loss terms. One loss term here, one loss term here, isn't it? And finally, see the same. Now observe one thing very interesting. The image is the one that is giving the grounding to the first encoder. This is the cross attention is in the encoder, but it is also giving a grounding to the decoder, isn't it? And this text is going to the decoder. The input text is going to the decoder, right? Both to the encoder, it's going to all the three pillars, isn't it?
Why the cross attention should have taken the ITM, right? The initial, the identified.
No, ITM is not the output. ITM is the loss term.
Oh, lost.
Right? But you just give it the image now to the decoder. It worked for their case, right? So, but you could argue, can I create a separate architecture in which I could have given like
whatever the
image grounded text to the decoder?
Yes.
Could I have given that? And what they found is they must have done experiments with all of that. What they just found is that it's better to give the original image to the decoder. Right? And when you do that, now you have the standard decoder loss term. So you have three loss terms and you do it with that. Do you see, guys, how this architecture works? So suppose now, so you train this machine with three loss terms, minimize all three loss, it gets pre-trained. Now let's see how would you do each of the separate tasks. How would you do unimodal embedding? You give it an image and this thing comes, sorry. How would I get an embedding from an image? All you have to do is go through the first pillar. You have your answer, isn't it? You want to just do text embedding, unimodal text embedding. That is your simple bird. Just pass it to the second pillar. It will do that, isn't it? You want to do image grounded text embedding, something that has learned from its adjacent image also. Then you would go through the third pillar because it is grounded in the image. The text embedding is not independent of them. It's a first multimodal. You see, it's a multimodal embedding of the text, right? And very good for text understanding. And the fourth pillar is your image grounded generation. text generation. So it is learning from the image, it's learning from the input text, both, isn't it? So for example, you can do visual question answer with it, isn't it? That's it. That is this paper, guys. And once you have this paper, you realize that, of course, it can produce good captioning for the images. Because what happens if you just don't give the text and you just give the image, but you look at the decoder? What will the decoder produce? It has to produce some text, even if you didn't give any input text. And that text would be the caption. So you can use it for captioning. If that caption happens to suppose, suppose you have an image, you don't know whether this caption is good or not. Do one thing in the inference phase, keep the caption in your back pocket, give the image, let it produce the caption. Now compare these two. If they don't match, throw away the old caption. You see that, right? And so you can improve your data, you can filter bad data, you can improve upon it and so forth. So that, folks, how many of you feel it is a beautifully done architecture? Very well done, right? Yeah.
Discuss the fourth pillar.
Fourth pillar is a decoder pillar. So decoder pillar, what it does is, see, it's like, think of it as your chatbot.
It's got the image vector. That's it, right?
That's right. It's got the image vector and the text vector. Right? So what it is doing is it's taking image and text. It is doing its cross attention, and then it is producing more text.
And
It's
the
a
cross attention is again.
It is exactly the same as this. See, if you look at this, right, this between these two, what is the difference? Just look at the difference. One is using bidirectional attention, which is what encoders do. And causal self-attention just means that, see, so causal is a interesting word. Suppose I have generated so far 3 tokens in my response. I have said the cow jumped. You would agree that besides the input, whatever I may have gotten, input text, I need to pay attention only to these 3 tokens. I need to feed that along with the input into the system, right? You see that, right? That's why it's called causal, because see, when you're generating task, not only the input prompt, but the words that you have generated so far, the tokens you have generated so far also matter. You see that, right? That's why these are called causal self-attention.
Causal self-attention is you only take the relevant words, tokens.
The generated tokens, so far generated tokens.
And where is that generated?
Here. This, right? This machine, what is it? This machine doing? It's a decoder. Remember, this is a decoder. Decoders produce text, right? So guys, let's think through this flow again. See, what happens is, suppose this thing, right, is, suppose this is a picture of a cow jumping over the moon. Right? Let's draw it out. Let me do that. You have a picture. Here's the moon, and here's your happy cow jumping over the moon, right? So, and so this is your image. Are we together? And let's give it a horn. Okay, and now
Content text also.
yeah, and you could give it text, but let's give it a text. What is the cow doing? Let's say we are doing the visual question answers. Input text. So input image, input text. Let's look at only the 4th pillar. In the 4th pillar, let us look only on the decoder pillar. So what is the decoder pillar doing? The decoder pillar, decoder. What does the decoder do? It has gotten 2 things. It has gotten the input text and it has gotten image, and associated with this, the KV. will come with it, right? Let us say cross attention. Now, what happens is that, think about it this way. Ultimately, decoder is a function, right? If a function is given an input, it is given two pieces of input, x and y. Let me just say x and y, or x1 and x2, because y is usually reserved for output. Let me call that the x text and x image, right? So this is a function of x image, x text. A function will produce a deterministic result, the same result over and over again. So it will produce the same softmax. Now you can sample of the softmax, doesn't matter. But unless you change the input, the softmax will keep producing the same output. So how does this machine, so it may produce, what is the cow doing? It may say the first word that it may produce. So it will, what you feed these two things in, it produces these logits. You pick the word. Let us simplify. Let us even throw away sampling. Let's say that you pick the most probable word. And the machine says that the most probable word is the. Now, unless you feed the word the, now you augment your input with the word the. In other words, you change x to xt prime, right? It will still produce the same logic. You need to append the newly produced token, isn't it? So you append the newly produced token. Now, let me call it T1 that has just gotten produced. T1. This time around, the word token cow lights up, right? The cow, and then you have to append it here. So do you notice it's causal? In other words, it is not arbitrary. It is caused by, the next output is caused by or depends upon the previous inputs. That's why decoders are called causal models. Right? The word causal model means literally as simple as that. That's all it means. Is it making sense?
ChatGPT also.
Yeah. They're nothing but decoders.
Decoder, yeah.
They're just decoders. I see the trouble is there's a lot happening in there. But basically, what we have found is you scale up the decoders massively, they develop abilities. Right? So between GPT-2 and GPT-4, for example, there is a lot of similarity. I mean, obviously, there's some new things, but basically, it's just a scale thing. Because, and I keep mentioning this thing, have you seen me mention the 1970 landmark paper, physicist paper? More is different. More is different. As you make models bigger and bigger and bigger, it is not the same thing anymore. It develops a lot of abilities and it starts doing things you wouldn't have anticipated. Right? I'm reminded in the movie Imitation Game, right? Alan Turing, who was trying to create AI, and he solved when he was given the task of, how many of you have watched that movie? And right? So he literally is responsible. If there is one man responsible for winning World War II, it would not be an exaggeration to say that more or less he single-handedly made the one breakthrough that handed Allies the victory. Alan Turing. And apparently tens of millions of lives were saved because of that, by every estimate. So he was not, people were trying to statistically break the code of Enigma. So the Germans had a machine called Enigma, which was remarkable. It was an encryption engine, and they would broadcast their message over the radio waves publicly. It was an encrypted message. People thought, okay, we'll decrypt it, except that nobody could decrypt it. And every day the code would change, right? So the old traditional way was using statistical analysis, and they were doing it all the time. It's a movie really worth watching, by the way. By the way, the book is even better. It's a lovely book, but they were not getting anywhere. So Alan Turing, when he joined that group, that very secretive team, everybody I mean, the story goes is they literally laughed at him because he was sitting in a corner thinking while others were busy doing actual work, like statistical analysis. He was there out there thinking, right? And he says, I'm going to create a universal machine that can solve all problems. In particular, he was after AI in his dreams, what today you would call AI. He wanted to create things like that. So there's a lot that happens, but at the end of the day, he does crack Enigma, right? And so the war was won. It's a fact that very few people know that the war was not won by soldiers. It was won by one mathematician. And what you call computers are Turing machines in a very literal sense. They are all working on Turing machines. So he got very attached. But there's a problem because it turns out that the government doesn't quite like him. It's hard to like open very free-thinking people. And on top of that, he's gay, right? Which is a crime in England. So he's like basically put under house arrest and so forth, and given all sorts of injections to cure him apparently of his orientation. So pretty sad story. He died very young, actually, very, very young. He changed the world and died pretty much. It's almost like he came to change the world, changed it, and then died. So in the very last days, there's a very interesting and touching scene. His old friend goes and meets him, and she notices that he's pottering around his machine. And Alan makes a statement that's very touching. He says, Christopher is becoming more intelligent every day. There are so many new abilities, so new things it can do now, right? And he's busy wiring and rewiring his machine. And I found that statement very touching because today he called his machine Christopher, is what he was making AI. And today, if you look at it, his dream has come true. Christopher really has become very intelligent, isn't it? So as these machines have scaled up, it has become very intelligent. So you know that there is a test for AI. We say a Turing test. What is the Turing test? How do you know if a machine has achieved artificial intelligence?
Not a human kind of.
No, basically what it has to do, there are many variations, but simply put, if it can convince a human being that it's not a human being, but it's not a machine, but a real human being. And if it is, imagine a Chinese wall, a curtain, and you're talking to it, and there's no way you can tell whether it's a human being or a machine, right? You know that it has achieved some form of artificial intelligence, right? People today call it the Turing test. But guess why the name of the movie was Imitation Game? Because the initial paper of Alan Turing was called Imitation Game, in which he introduced the concept of the Turing test, right? And so today, have these machines achieved some semblance of artificial intelligence, genuine artificial intelligence? I'll give you a fact. When Alexa came out, and it's been many, many years now, when Alexa came out, and this is a fact, every day, a dozen or so people were proposing to Alexa, proposing marriage to Alexa, right? Because no matter how much you tell them that this is not a real human being, right? No, I'm not kidding. They couldn't, it's not possible. The level of wisdom, the level of humor, the empathy, no, you don't find even in the best of your dates. Right.
Wait for AGI.
What's that?
AGI.
Yeah.
Personal assistants are already coming.
Right. So you know, what we do is every time machines achieve a certain level of artificial intelligence, we move the goalpost because somehow we are very resistant to acknowledging that these machines have really achieved intelligence. Yesterday, I posted on LinkedIn an article. I encourage you to read it. It's a humorous article. Okay? And you might have some fun. In the break, please do read my LinkedIn article. Actually, I'd appreciate it if you do that and post a comment or repost it. But anyway, please do that. And you will see what I mean. And it is very contextual. So, well, see, these machines are now able to caption. And we are going to do one more paper today. Are you in a mood or you want to run home? You need to go home so soon. Okay. How about this? Let's have a halfway situation. Have your coffee. Read this paper, guys. Sit here and read this paper. By now, you would agree that the paper is straightforward. Should become straightforward to read after this explanation. Right?
You want to talk about the Turing Awards?
Hmm?
The Turing Awards that are given. At least.
Oh, yes, yes. The highest award in our field are named after Alan Turing. But Alan Turing, if I'm right, he died. He committed suicide at 40 or 41. Because those were conservative times, gay behavior was not tolerated. And anyway, he was, even without that, he was considered weird. Right? He was considered like he was an outlier. And he did everything differently. And people don't like people who do things everything differently. Right. So
And the Turing Awards are given in the city of Turing.
that is true, the highest award. So the great godfathers of our field, Geoffrey Hinton, Jan LeCun, Bengio, they all are Turing Award winners. Right. So there was a very humorous incident, but I'll tell you about it. Let me stop the recording.